Good afternoon, everyone. Today we will talk about chapter 5, section 2, the volumes. In the chapter 4, we discussed how to evaluate the area under curves, right? Under the function curve. Now, in a similar way, we will discuss how to evaluate the volume in this section. Now let's start with the motivation here. So here the picture shows the Great Pyramid of the King Khufu in Egypt, which has a long history. And we need to find out the volume of the pyramid, like this one, okay, like this pyramid model. And we have already studied several volume formula in the high school, like the rectangular box, a cube, a cylinder, as well as a cone, right? But we cannot use the hands-on formula to deal with the volume of some solid we will discuss in this section. So our motivation starting from here, okay? From here we have a solid looking like a pyramid. How can we find the volume? Or we can formulate the problem in a more general way, like those, okay, like this solid. We can formulate the problem in a more general way, how to evaluate the volume of the sweet potato shape, like this one I placed in the XOY coordinate. Okay, now let's check that. Okay, since the solid is looking like a sweet potato, that's what I called. Okay, that's what I called here. Of course, it's in a 3-dimension. Okay, it's in a 3-dimension, and I placed my sweet potato in the XOY plane, and the left side is ended on A, the right side is ended on B. And for example, if you use your knife, okay, if you use a small knife to cut the sweet potato at some position X, right? Maybe it's not middle, okay? It's not in the middle, just some position between A and B. So when you cut the sweet potato, you will get a cross-section region, right? You are going to get a cross-section region, and at the point X, it might looks like this region, okay? This region we shaded in the red color, and let me just bound it here, okay? Let me just bound it here. So that might be the shape, how the shape looks like when you cut the sweet potato, the cross section, right? And we know this cross section is perpendicular to the x-axis, and it forms a plane. So we will call this vertical plane is px, big px. Okay, that forms another plane which is perpendicular to x. So we will call this plane is px. So another example, okay, another example to get the cross section, region. So for especially at the endpoint B, okay, at the endpoint B, of course, the right side, the cross section region will be this one. Let me just bound it, use a different color. Let me choose blue. So this is how the bounded region for the when we have the endpoint, when we at the endpoint B, okay, when the solid placed at the endpoint B. So that is the small part, right? The cross section will be smaller than the the cross section region at the X. And also you can get the cross section at the endpoint A. So if you use a knife, to cut the sweet potato, then it's easy to get the cross section region, right? So here we can using knife to cut the sweet potato, which means this solid, okay, to cut the sweet potato at the point X, okay, at the point X. Use a knife to cut the sweet potato at the point X. Then the cross-section region or we call it the cross-sectional region. This part we are trying to understand what is the cross-section region here. The cross-section region is shown in red color, right? In red color. And I also bounded this region with the red pen, with my red pen, right? And this region forms a plane, lies this region lies in a plane we will call it PX, okay, PX lies in the plane PX. And what is PX? This is a plane perpendicular to the x-axis, right? So, and you will notice that as you shift in your life, when you use the knife to cut the sweet potato, when you shift your knife from A to B, you will, when you cut at a different place, then the cross section looks different, right? Like here, when x equals b, that is the blue pen shows the cross-sectional region, very smaller one, right? And at the x, the cross-sectional region is much bigger than the AB, right? Now let's illustrate what is this AX I put here, okay? What is AX here? But try to understand this is the solid in 3 dimensions, and when you place on the x or y plane, when we use a knife to cut at some position, you get the cross section. This plane is perpendicular to x-axis. Now let's check the solid again. Check the notations. For the solid S, the x is between A and B, right? We shift the x from A to B. And what is this x? This x is the area of this cross-sectional region, okay? This area denotes this function ax denotes the area of this cross-sectional region, and of course it will change, right? AB is much smaller than this ax. It will change as you shift your x on the horizontal axis. So AX, we define this big AX is the area of the cross section at point X, and it will change, it will be different, vary as X increases, right? As X increases. And what is this PX notation? That is the plane, right? That is the plane at the point X, which perpendicular to the x-axis, right? Which is perpendicular to the x-axis. So here we have the solid, okay? We have the solid looking like this one, and we figure out what is the cross-sectional region, and we define the area. The area of the cross-section is a function ax, and we understand as x change and as x is varies from A to B, the area function will be different, right? Then how can we get the volume? How can we get the volume for this solid? We were starting from the idea here, okay? We were starting from the idea. So here we are going to cut, okay? We are going to cut the sweet potato into n pieces, okay? Cut the sweet potato into n pieces. Cut the sweet potato into n pieces, okay? Into n pieces. And with the equal thickness, I will call it delta x, okay? They has a little thick, so you will get a piece like this one, okay? Shaded in the red color. So they have a little thick. What is this delta x? Of course, it's the same. B minus A over N, right? It should be, again, B minus A over N. And here, from A to B, we can still form N subintervals. So subdivided AB into N subintervals, like what we did in the previous chapter. So subdivide number 1, number 2, then we can still subdivide the interval AB into N, right? Into N. And then we can write it as x0, x1, x2, x3, and so the ith one will be xi minus 1 until xi, and the last one, right? Like that. The last one will be xn minus 1 until xn. Let me write it. Xn minus 1 until xn. And in the next step, let's looking at how we estimate the volume for the ice slab, or you get, we will call those each slab, okay? Each slab. So this one is this piece is some cross-sectional region, right? Some cross-sectional region, and with a little thickness, right? With a little thickness. Then in the ice subinterval, this is showed the ice slab, okay? The ice slab in the ice interval xi minus 1 to xi. Then we can choose the xi star, which is the sample point again, okay? So xi star is still sample point in the ice subinterval, okay? In the ice subinterval, sample point in the ice subinterval xi minus 1 to xi. So how can I get the volume of this ice slab or this ice piece, okay? This ice piece of sweet potato. So I can use the base area, okay? I can use the base area. Let me bound it. I can use this base area times the thickness delta x, right? I can use the base area times the thickness. It works similar like the cylinder, okay? Cylinder. I can use the base area function a here, but what is the area here at the So in the I subinterval, it's better to choose the xi star, right? It's better to choose xi star, and we understand the sample point is any value you can choose in the I subinterval. So I choose I get the area function. I evaluate the area function of the cross section, this region. I can call it as a base, okay, as a base. Then add the xi star, and then times the little thickness delta x, right? Times the little thickness delta x. Then I can get the estimated volume for the ice slab, okay, for the ice slab. Now let's check that, okay? Let's check that. Choose the sample point xi star in the ice subinterval. Then the ice slab volume can be estimated by the formula. Let me just write, okay, the VI, we call it VI, the volume, okay, the volume can be estimated as the base area times the thickness. Base area times the thickness of the slab, which is delta x. And we know when you cut the sweet potato into n slabs, you make sure your thickness are the same. Okay, each piece's thickness are the same. So base area times the thickness. The base area will evaluated at the sample point x star, and then times the thickness delta x. So we can form the volume formula. Okay, the volume formula, the estimated volume for the ice slab in this way, and we understand this is the cross section area, right? Cross section area evaluated at xi star, and then times this little thickness, right? Times little thickness. That is the estimation we use, not equal, approximated. Okay, approximated. And to understand this idea, okay, to understand this idea, actually we can add the sum of all those. Let's come back, right? Let's come back. So this is the volume for the ice slab, right? Ice slab. So I can estimate the volume. For example, okay, for the first piece, okay, for the first piece, I can estimate it as the cross-section area at the x1 star times delta x, right? I can estimate the second piece's volume with the area cross-section area x at x2 star times the thickness, and until the last one I can estimate the nth piece in this way with the base area, the area function evaluated at xn star, which gives the cross-section area times the little thickness, right? And if I take the sum of all those n pieces, if I take the sum of all those n pieces, then I can write it as a Riemann sum I from 1 to n with the area function axi star times delta x, right? So if I take the Riemann sum of the volume for each pieces, then I can approximate it by volume for the sweet potato in this way, right? In this way. So that is the idea, okay? That is the idea. Now let's check this graph, okay? Let's check this. This is the graph. I just use my knife to cut into 7 pieces, okay? I just use my knife to cut 7 pieces. So we get 7 slabs here, okay? 1, 2, 3, 4, 5, 6, 7. I got 7 slabs here. Again, it's still we place from A to B, right? From A to B, and equal weights, equal thickness we called, right? Equal thickness will be B minus A over N, right? B minus A over 7. So the right side, this graph means we cut into 7 pieces we cut the sweet potato in the 7 pieces to get the volume of these 7 approximating sum of these 7 approximating slabs volume. That will be the estimation of the volume for the sweet potato on the left side. So we get the thickness for each slab, which is b minus a over delta x. And also we subdivide the interval, the closed interval ab into 7 subintervals like here, right? x0, x1, x2 until x7 equals b, right? Until x7 equals b. Now we can check the last, okay? We can check the v7, okay? We can check the v7 here, okay? V7 here. So V7 is this slab. Okay, we use the 7 slab, and this is the cross-sectional region. And we understand the cross-section area are different, right, in those 7 pieces. And this one has the largest cross-section. This one, okay? This one gives the largest cross-section area. Make sense? And we can shade it in this way. Of course, the 4th lab has the largest cross-section area, right? And we can call this one is AX 4 star, okay? AX 4 star. So let's looking at the last one, okay? The last slab. So the cross-section area, okay? The cross-section area will be AX7 star, right? AX7 star. We evaluated the cross-section at the sample point x7 star, okay, x7 star, and then the thickness, okay, the thickness of this slab again is delta x. So we can estimate the number 7th slab for the number 7 pieces of the sweet potato. Use the base area, right? The base area, which is the cross-section area, evaluated, the area function evaluated at x7 star, then times the little thickness, right? You get the volume approximated. You get the volume of the 7th slab. And then again, if we take the sum of all those 7th slab. Why you comment is beautiful potato? So did you understand? You cut the potato in this way, and you use 7 slabs volume to estimate the sweet potatoes volume. Try to understand, okay? Try to understand. So if I take the sum of the 7th slab from the right side, okay, from the right side, and each area function is evaluated at the xi star, which gives the base area times the thickness. Then we can evaluate it or approximate it the volume of the sweet potato in this way using 7 slabs. Okay, and we understand it's an approximation, right? It's an approximation. If you increase the number of the slabs, that will be the Riemann sum will be more accurate, right? The Riemann sum will be more accurate. So the total volume is approximated by the n terms, okay, n Riemann sum of the I slab volumes, okay, I slab volumes. And we can check here, okay, we can check here. If we increase the number of n, like the before, okay, like before we discussed. Let's review for the chapter 4, okay? Let's review for chapter 4. Now here we understand the volume can be approximated by the Riemann sum of n slabs volume, right? Now let's review for the chapter 4 how we define the area. Okay, how we define the area. Don't write you feel sleepy, you feel hungry. Those comment as 弹幕. Okay, it's negative. Okay, it's negative. And I also feel tired and sleepy. Okay, so don't disturb me. Try to give some positive and excited comment and catch up what we did today. Okay. And you should be more responsible and independent for your own study. Okay, for your own study. So let's review for the area under one function curve. Okay, the area under one function curve. So we can use the n approximating rectangles, take the sum of n approximating rectangles area to estimate the area. Okay, area under the function curve. So the area can be represented, can be defined in this way. The n approaches infinity, right? The n approaches infinity. Then take the Riemann sum, okay? Take the Riemann sum. Fxi star times delta x, okay? Times delta x. So that is the ice rectangles. Then take the sum, take the Riemann sum, and we let n approaches infinity. That means you increase the number of rectangles, right? So in this way, we understand the fxi star is the height of the ice rectangle, right? The height of the ice rectangle evaluated at xi star. As I said again, don't put any negative or upset comment as 弹幕 which disturb my teaching, okay? Which disturb my teaching. So here, that is the fxi star, okay? fxi star. fxi star, which gives the height for the ice rectangle, right? And evaluated at xi star. So here, this fx, we know the area can be defined as a definite integral from a to b, right? From a to b. And what is the integrand here? This integrand fx shows the height, right? This fx shows the height. Now let's check the volume. We can approximate it, okay? Let's check the volume before. We estimate the volume of the sweet potato by the sum of n slabs, right? By the sum of the n slabs volume, axi star times delta x, right? And then actually we can also, similar way, we can also define the volume as the limit when x approaches infinity, okay? When x approaches infinity. Sorry, should be the Riemann sum. Riemann sum. So should be the limit of the Riemann sum 1 to n a xi star delta x, right? Now here, what is my axi star? What is this function axi star comparing with the here? So here the axi star will be the cross-section area, right? That is my function ax, right? It's a function, so will be cross-sectional area of the ice slab, right? Of the ice slab evaluated at the xi star, right? At the sample point xi star. So it's much clearer, okay? It's much clearer. So my ax is the function, right? Is the function. So can we do the similar way to define it as my integrand becomes the cross-section area? as a definite integral. Also from A to B, we place the sweet potato in the XY plane from A to B for the x as an independent variable, right? So similar way here, but the integrand x represent ax represents the cross-section area function, and we know as x changes the function, the area of the cross section will be different at the point, right? Now let's check the definition of the volume. Let S be a solid that lies between x equals a and x equals b if the cross-section area of the S. Okay, we know the cross-section area forms a region which lies in the plane PX. Okay, through the X, and this plane is perpendicular to the X-axis. But we call the cross-section area is a function AX. Of course, this A is a continuous function. Then we can evaluate the volume of the solid S. Okay, it's not the region again, it's in the 3-dimension, it's a solid. Okay, the volume of this 3-dimension solid can be written in this way. Sorry, it's still a typo here. Okay, it's a typo here, should be the volume. Okay, should be the volume. So that is the limit of the Riemann sum. Riemann sum, which means the sum of an approximating slabs, right? Slabs, and then we can write it as the definite integral with the integrand as ax, the cross-section area function, right? Area function with the independent variable, it's x, right? It's the area function of the cross-section. That is the integrand. So from here, it becomes much easier if we define it as a definite integral. For example, if we know the cross-section area function is pi x squared, if we know the ax, for example, if we know the cross-section area is the function pi x squared, then it would be much easier. It would be much easier to evaluate the definite integral to get the volume of some solid, right? And in this section, we will focus on the example with the solid you obtained by rotating some region. Okay, it's called the volume of some rotating solid. Especially, it's not as difficult as the sweet potato. Okay, sweet potato. Now let's check the sphere. Okay, the solid sphere. How can we estimate the volume in this way? And let's recall the volume of the solid sphere if we know the radius. If we know the radius, here the radius is with 1. Okay, let me write here. Okay, let me write here. So for this example, okay, for this illustration, if the radius of the sphere r equals 1, then we know the volume. Okay, then we know the volume is v equals, the formula is 4 pi over 3 r cubed. Since my r is 1, so will be 4 pi over 3. Okay, this is example when the radius is 1. Okay, when the radius is 1. So the first one, I use 5 disks. Okay, 5 disks to estimate the volume of the sphere, a solid sphere. Okay, and each one is the cylinder actually, right? Cylinder. So now, yeah, of course, the radius will change for here. The radius will change for each slab. But I'm talking about if we know a solid sphere with the radius r, okay, with the radius r, then we are going to estimate it. Okay, the radius for the cross section area circle, that will change. So what is the cross-section region looks like? Can you tell me that? What is the cross-section region looks like? Of course, it's a circle, right? And the circle will be different, smaller, greater, right? Will be different cylinders with different circle, right? Different circle with different radius, right? With different radius. Okay, I saw some reply. Very good. Okay, very good. So here we use 5 cylinder to estimate the volume of the solid. We know it's less accurate. Okay, it's less accurate. Now we increase the number of the discs. Now we have 10. So you will notice that each cylinder gets thinner, right? Gets thinner. And again, the cross section region also shows a circle, right? Also shows a circle, and the circle will be different. That means the area function of the cross section will be different, right? Will be different. So using 10 discs, the volume is the sum of those 10 cylinders. That is this number 4.2097. And then I increase my number of discs into 20, then from here you will notice that if we increase the number of the slabs, okay, that will be more accurate, and the solid will be more accurate to the solid of a sphere, right? And of course the number will get very close. The number will get very close to for the this number will get very close. This number will get very close to 4 pi over 3 as we increase the number of discs, right? As we increase the number of discs, we'll get close, okay? Get close to this number. That is the actual value for the for the solid of a sphere, right? So the number you get, you evaluate it for the volume here, that will be more close to this one, right? And we know the formula is 4 pi over 3, right? We know the formula is 4 pi over 3. So here, that means you increase the number of solids, okay? You increase the number of the slabs, that will be more accurate. And we can use the definition, okay? We can use the definition from definite integral ax dx. So here the cross section area, if we can figure out the radius, okay, the radius for each cross sectional region circle, then that will be easy, okay? That will be easy, okay? That will be easy. Here is the one I'm giving, okay? Is the giving information, the radius, okay? Here is the radius I'm giving for a circle, okay? For a sphere, okay? For the sphere. So from here, from the definite integral, if we know the cross-sectional area function, then that will be easier to evaluate the definite integral. Then we can give the answer for the volume. And this since here the cross-sectional region shows a circle, so that will be pi times radius, right? Times the radius. And later you will see the notation. We are not going to use r for the radius because this radius will change. This radius will change as the x change, right? It's not x again, and we will check it specifically. All right, it's almost time. Let's take a 5 minutes break, then we will continue on the examples.